welcome to the deep dive. If you're looking to be the most informed person in the room, well, you're in exactly the right place. Today we are digging into something truly massive. It's the unveiling of a ship called Hull 096. And this isn't just another ship. The builders are claiming it's the largest battery electric ship in the world. And get this, maybe the largest electric vehicle of any kind on the entire planet.
That last claim, that alone tells you the kind of scale we're talking about here. We've been digging through everything we can find on this, reports from the shipbuilder, Incat Tasmania, some deep technical analysis from engineering journals, and what EV specialists are saying.
So our mission today is pretty clear. We're going to unpack this historic milestone down in Australia.
Yeah.
We'll dissect the power system, which is just immense 40 megawatt hours. And we'll try to figure out what this all means, for the future of shipping. Is this a one-off, or is this the start of a real pivot for the industry?
Oh, it's absolutely a pivot. I think we're moving past the era of just small electric ferries. We're now in the territory of high-capacity, really high-performance vessels. This ship, it's a huge shift in the engineering, and the details are just fascinating.
Okay, so let's ground this for a second. Let's go to the moment it actually happened. We're talking mid-December 2025 in Hobart, Tasmania. The big milestone was the first successful trial of the e-motor system.
And that trial, that was the real moment of truth. Hull 096 powered up and ran on the largest battery electric propulsion system ever put on a civilian ship. And critically, it was sailing entirely on stored energy. This wasn't some kind of hybrid test. This was the first time a ship of this size, this weight, carrying 2,100 passengers and over 220 cars, had run on 100% battery power. It's a new global benchmark.
The Incat chairman, a guy named Robert Clifford, he called it a remarkable achievement, a turning point. But I want to go back to that claim. Largest electric vehicle of any type. How do we quantify that? Are we talking bigger than one of those gigantic mining haul trucks?
Yeah, that's a fair question. The largest EV claim is usually about the total physical size and the sustained power output. It's not necessarily about the raw torque you'd see in a mining truck, but when you consider its length, 130 meters, and that it can move thousands of tons of people and cargo at high speed, it definitely qualifies as the largest vessel ever powered this way. It just sets a new ceiling for what's possible.
And Tasmania itself. It seems like the perfect place for this to happen. They're not exactly new to this kind of ship design, are they?
Not at all. Tasmania has been a world leader in aluminum shipbuilding for decades. They really pioneered using those lightweight hulls for high-speed catamarans. So this achievement, it really just confirms their pivot to leading the next era of, sustainable high-performance ships. They know how to build big, fast ships. Now they've proved they can electrify them.
All right, let's unpack the engine room. Or maybe we should call it the battery room. Because the physical size is impressive, sure, but the scale of the power system inside, that's the real technical story here.
Absolutely. The energy storage system, the ESS, is the heart of this thing. It delivers over 40 megawatt hours of capacity. And for comparison, our sources are confirming this is 4 times larger than any maritime battery ever put into service before.
4 times the previous record.
4 times. It's an enormous leap.
And when you have that much electrical potential stored in one place, the weight must be just monumental.
It is. The battery systems alone weigh over 250 metric tons. That's about 275 US tons. And it's not just one big block of batteries. The engineering complexity is all about safety and performance. We're talking about 5,016 individual lithium-ion batteries.
5,016. Wow, so why break it up so much? What is that arrangement? 12 sets of 418 modules spread across 4 separate compartments. What does that tell us?
It tells us 2 main things: redundancy and safety. First, by putting them in 4 separate areas on the ship, you prevent a fire, a thermal event in one section from spreading. And second, organizing them into 12 sets lets them do incredibly detailed load balancing and monitoring. If one set has an issue, they can just isolate it without affecting the ship's operation. It's all about uptime and security.
And here's where it gets really interesting for me from an engineering perspective. Thermal management. You pack 40 megawatt hours of lithium-ion batteries into a ship. Heat is your enemy. Thermal runaway is the big fear. How did they solve that?
Yeah, the technical deep dive from iSpectrum was super clear on this. The cooling system is incredibly sophisticated. Instead of one big centralized cooling system, they use air cooling, but with an individual fan for each module.
Wait, a fan for every single module? This seems incredibly complex, but also absolutely necessary.
It is necessary because the main safety focus is what they call single cell isolation. It means if one single cell starts to overheat, that catastrophic process called thermal runaway, that event is stopped from spreading to the cell next to it, or to the whole module. That level of isolation, backed up by the fan per module cooling, is really the only way you can safely operate a battery system this big.
So we've got this Australian-built, high-tech powerhouse. All that energy gets channeled into moving the ship. What's the propulsion system like?
The power goes to 8 axial flow water jets, which are driven by permanent magnet electric motors. So if you're picturing a big traditional propeller, forget that. Water jets are basically just powerful pumps that suck water in and shoot it out the back at high velocity.
And why jets instead of a propeller?
For a ship like this, a fast ferry with a lightweight aluminum hull jets are just very effective. They're efficient at high speeds, and crucially, they don't need as much water depth to operate, which is a huge advantage for the route it's designed for.
That sets us up perfectly. Let's talk about that mission. Because this advanced Australian ship isn't staying in Australia. It's heading for South America. Who's the operator and what's the route?
The client is a big South American ferry operator, Buquebus. And here's a surprising detail our sources found. Hull 096 was originally going to be powered by LNG liquefied natural gas. It was even going to be named the China Zorilla.
Hold on. That's a huge change. A lot of the industry sees LNG as this necessary bridge fuel, to lower emissions. To pivot from a major fossil fuel project like that to 100% battery electric, that's a massive statement of confidence.
It's a huge statement. It shows that the economics and the tech for marine batteries changed so much during the pandemic that the electric option just became better for this specific route. And that permanent route will connect Buenos Aires in Argentina with Colonia da Sacramento in Uruguay right across the Rio de la Plata estuary. It's about a 60-kilometer trip.
90 minutes for the crossing. That's quick. And that 90-minute segment is exactly why ferries are such a good fit for electrification. High turnover. But that whole model falls apart if charging takes forever. How are they refueling 40 megawatt hours of batteries?
That's where the whole system of systems idea really comes into play. They're installing dedicated DC fast charging stations at both ports. The goal is a full recharge in just 40 minutes, which is actually less time than it takes to load and unload all the passengers and cars.
40 minutes to pump in over 40 megawatt hours of energy. The power demand on the port must be astronomical. You'd need a dedicated substation just for the boat.
Exactly. You're not just plugging this thing into a wall socket. We're talking about pulling megawatts from the grid in a very short amount of time. And that brings up the real question of sustainability, right? Where is that power coming from?
The ship was tested in Tasmania, where the grid is 100% renewable. That's great. But what about its permanent home?
This is a really critical point. Uruguay is actually a world leader in clean energy. Their grid is over 92% renewable, mostly wind and hydro. So when the ship charges in Colonia, its emissions profile is genuinely close to zero.
But the other end of the trip in Argentina.
Argentina's grid is more of a mixed bag. They have a good amount of hydro, wind, and nuclear, but it's still dominated by natural gas. So when the vessel charges in Buenos Aires, it's not really zero emission. It's more like it's shifting the emissions from the ship's smokestack to a power plant on land.
That's such an important bit of nuance. The ship cleans up the local air in the port, for sure, but its total carbon footprint really depends on the grid it's plugged into.
Precisely. It really highlights that electrification is only as clean as the grid that's powering it.
So let's connect this back to the wider industry. Why is this such a breakthrough? But at the same time, why aren't we seeing this on, say, a huge container ship crossing the Atlantic?
Well, the short ferry route is the ideal use case, like we said. The rapid charging, the predictable schedule. It all just works. And this project was possible because of 3 things coming together: better battery density, more efficient electronics, and the industry's acceptance of lightweight aluminum hulls.
Tell me more about that aluminum advantage. How does that play into the whole battery equation?
It's absolutely critical. An aluminum ship weighs about half as much as a comparable steel ship.
Half.
Roughly half. So you're already cutting your energy demand in half before you even install the battery. That weight saving is what makes carrying a 250-ton battery pack even feasible.
But if they can build this now, a 130-meter electric vessel, why isn't the whole global shipping fleet going electric tomorrow? What's the limiting factor?
The limiting factor is still, unfortunately, the basic physics of energy density. Even the best lithium-ion batteries, they don't come close to the energy you can store in diesel fuel. For a long-haul trip, say a 30-day journey across an ocean, the sheer weight and volume of the batteries you'd need would displace so much cargo that it just wouldn't make any economic sense. You'd have a giant floating battery that couldn't carry much else.
So it's still that system of systems challenge.
Hmm.
But financially, for a ferry route, how do the numbers stack up? It has to be a massive upfront cost.
Oh, it is. The upfront cost for the 40 megawatt hour battery system and those high power chargers is very high. But you offset that with huge long-term savings. The studies we've seen show fuel savings over 60% compared to diesel. And your maintenance costs are way lower. Electric drivetrains just have far fewer moving parts than a complex diesel engine.
That sounds like a clear win. But what about the lifespan? A ship can last for 40 years. What about that hugely expensive battery pack?
That is the crucial calculation. The ship itself might last 40 years, but the batteries will need to be replaced probably every 5 to 10 years, depending on the charging cycles. And a 40 megawatt hour replacement pack could cost tens of millions of dollars. The operator has to factor that cost in every decade, which really changes the long-term return on investment.
It changes the risk profile, yeah. But clearly, the industry is moving forward anyway. You said Incat is already building more.
Absolutely. Hull 096 proved the concept, and Incat is running with it. They've already signed contracts to build 3 new, slightly more powerful 45 megawatt hour ferries for a Danish operator. So the trend is set. High-performance electric shipping is officially here.
This deep dive has been absolutely riveting. We went from this bold claim, the world's largest EV, to understanding the incredible engineering needed to manage that much power, right down to a fan for every module. We looked at the genius of the rapid charging model and the critical importance of where that energy actually comes from. So it isn't just a ship, it's a blueprint.
And it's a blueprint that's going to evolve in real time. What's so fascinating is that Hull 096 is now essentially a giant floating laboratory. The real-world data it's going to generate on battery health, on efficiency, over thousands of charging cycles, that data will be vital. So here's something for you to think about. What specific design changes, maybe in battery chemistry, maybe in charging infrastructure, will this stream of data prove we need for the next generation of mega electric transport? The lessons learned here won't just inform the next electric ferry, but maybe the next electric train or even heavy-duty electric trucks.
That's a powerful thought to end on, that the future of land transport might be shaped by data that we collect at sea. Thank you so much for joining us on this deep dive, where we turn complex reports into knowledge you can use. We really hope you'll continue to follow the channel to get more in-depth breakdowns just like this one. Until next time.